Hello everyone, welcome to my channel Code with Sunny, and today I am going to discuss the problem the weighted graph of April Easy 2021 of Hacker Earth. Okay, so let's discuss the problem now. We have been given a complete graph with n nodes. Okay, so first let's read out the question, then I'm going to explain. There are two values associated with each node I, that is ai and bi, and then the weight of the edge between the two nodes is I and j, denoted by wij. It should be the modulus of ai bj minus aj bi. Okay, and find the sum of the square of the weights of all the edges, that is formally this value. Okay. Now you can see this question is not a question of related to the graphs. It is basically question of mathematics, that we need to solve this equation and find out the sum efficiently. We can use the brute force, but it is not going to be valid, because you can easily see n is going to be, if you look over the constraints, n is going to be at most 10 power 6, and if we use the nested loop, it would always give the TLE verdict. Okay, because the number of iterations will cross 10 power 10, which is actually not acceptable within the given time limit. Okay, so we have to print this integer, that is answer to this sum modulo this prime number. And how we are going to do that? Okay, so first let's read out the input format. N is given as the number of integers for ai, that a1 up to an, and for b1 up to bn we have been given ai to up to an and b1 to bn also. Okay, so first so how we are going to do this problem, and what should be the best way to solve this problem, yeah, using the you can say the any logics behind this question. Okay, so let's understand this problem in detail. Okay, you can easily see I have taken w as ai bj minus bi aj. Okay, now we have to compute w square. Okay, yes, I have to compute w square. Let me look over it once again. Yes, wij square for every I up to n, and for every I we have to iterate j from I plus 1 to n. Okay, now you can see I have to first understand this term, that is w square. Okay, so this is modulus, there is a modulus sign over this subtraction, and if we do w square, you can easily see it would be like ai bj whole square plus bi aj whole square, and twice of ai bi and aj and bj all are multiplied. Okay, now okay, consider n is equal to 4. Okay, so I am going to just explain this with the help of example. There is a pattern. Okay, so let me explain in brief. uh, we are not going to understand what is happening in this question, because we need to compute the sum efficiently. Okay, now how we are going to compute this sum, there must be some trick involved in this computing the sum. Okay, so let's do that for few example cases, that is n equal to 1 2 3 4. You will get the that is the trick that is being involved to compute this sum in o of n time. Okay, so let's find it out with the help of some example. So I have taken n as 4. Okay, now we have to iterate from I from 1 to I up to n for n, and for every I just iterate j from I plus 1 to n. Okay, now I am just keeping I as 1, and let's iterate for j from 2 to n. Okay, so I will have like a1 b2 minus a2 b1 whole square, and a1 b3 minus a3 b1 whole square, and a1 b4 minus a4 b1 whole square. Okay, now this is a modulus sign, it doesn't matter, as I've already explained, it will be opened like this. Okay, now you can see if you open this like this term, you will get the sum exactly equal to this term. If you arrange these terms very much carefully, that is club a1 square common from all these terms, it would be like, if you club a1 square common, it would be like b2 square b3 square plus b4 square. Okay, and if you club b1 square, it will be like a2 square a3 square and a4 square, all are common to b1 square. Okay, and this will be like sum. Okay, and what would be the negative term, because a square plus b square, or sorry, a square minus b square would be like a square plus b square minus twice of ab. Okay, so I will have a negative sign, I will have a common of twice a1 b1 and a2 b2 and a3 b3 and a4 b4 are common to this term, twice of a1 and b1. Okay, so this is for I equal to 1, and what should be for I equal to 2, because we need to compute I from I equal to 1 to n. Okay, so let me copy this one, and let me try to paste this again and just modify something. Okay, so I am just making it 2, and if I make it 2, I will be iterating from okay, so I will be iterating from A2 and from A2, and it will go from B3. Okay, so I will be just modifying one thing. So because I'm not going to use this statement, that is, this is no longer useful. So I will be just using, okay, A2 will be A2 B3, and it will be like A3 B2, and again I will be having like A2 B4 and A4 B2. Okay, so if this that is A2 B3 minus A3 B2 square and A2 B4 minus A4 B2 square. Note that I am iterating from j equal to 3, j equal to 4 up to j equal to n, which is 4. Okay, so if I club A2 square common from the above term, it would be like A2 square, and it will iterate up to B3 square and b3 square plus b4 square, and if we club b2 square common, you can easily see I will be doing like a3 square plus a4 square. Okay, so I have written this statement clearly. If you are not going to understand it, just expand this a2 square b3 square plus a3 square b2 square plus twice of a2 a3 b2 b3. Similarly, this term a2 square, you can easily say I'm talking about this term. Okay, a2 square b4 square plus a4 square b4 a4 square b2 square minus twice of a2 a4 b2 b4. Okay, now okay, so this is gone, so I'm just going to replace this a2 and this b2, and similarly this term will be gone. Okay, so this is for I equal to 2, and what about I equal to 3? So for I equal to 3, I need to copy one thing more, that is this one, because there is just a slight variation in this one, and the exact remaining things are exactly same. Okay, so I need to copy this. Okay, so I am going to paste this once again. Okay, so if I'm going to take is2, I need to iterate from, okay, sorry, I have is3, I need to iterate from j equal to 4 only, so only this statement is gone. So I will have A2 B4. Okay, sorry, this is not A2. One, no more A2. I will have A3 B4 minus A4 B3. And if I do square of this one, I will be having like A3 square into A3 square into and something like B4 square only. Okay, and all these terms are gone. And similarly, B3 square and the rest of the term is only A4 square common to that. Okay, so let me do one thing more. Okay, so I have only twice of A3 and B3, and similarly I will have only A4 B4. Okay, so this is the term that is coming up. For I equal to 4, you can see this term is going to be vanished, and similarly this term is going to vanish. It will become 0, so no need to compute. Okay, so for n equal to 4, I need to compute for I equal to 1, 2, 3, and you can easily see in the reverse manner, if that is for I equal to n minus 2, I will have like sum equal to uh, a of n minus 1. Okay, so let me generalize this case. For if I have a one based indexing, then I can have for I equal to n minus 1, that is 3, I will have place a of n minus 1 square into the sum starting from a of n minus 1 square into sum starting from b of n square to b of n square, that is only one term, plus this b of n minus 1 square into this sum starting from a of n square up to a of n square, that is only one term, minus you can see this term twice of a of n minus 1 into b of n minus 1 into the product, that is a of n into b of n. Note that the one thing that is common is you can see these terms a4 b4 and a4 b4 and a3 b3 and a4 b4 a3 b3 and a2 b2, and you can see yes, that is all about. And one thing, you can also see this sum, that is the coefficient of b3 square, you can see a4 square, and when in case of I equal to 2, it will come as b2 square, and the coefficient will become a4 square a3 square, and in case of I equal to 1, b1 square, and a4 square a3 square and a2 square. So it gives me the idea that we can compute this sum easily, and we need to compute only three things. Starting from I equal to n, I need to compute only three things, that is a4 square, that is product of AI and BI, and and the sum of, okay, so sorry, that is sum of AI and BI starting in a reverse manner, that is I equal to n to I equal to 1, and the sum of AI square, and you can also see sum of bi square up to I equal to n. I need to have like suffix sum of ai square, bi square, and the product ai into bi. Then we can compute for every I this sum efficiently and sum up all these. Okay, so this is the main trick. If you are going to expand this like that, then you are going to see the observation, that is the term that is going to be multiplied by. If I am taking I as 2, let's suppose I am taking I as 2, then you can see the sum of that is coefficient of a2 square. You can see that is it is coming like sum of all the terms, that is bi square starting from I equal to 3 to n, that is suffix sum of squares of bi. And if I'm talking about coefficient of you can see bi square for every I, it will be like suffix sum of I starting from I of j starting from I plus 1, and suffix sum of squares of ai. Okay, you can see if I have a I1, a2 square, a3 square, and a4 square. Okay, and similarly like that. So how we are going to compute that efficiently? Okay, let's head over to the code and find it out, what is the best implementation of this problem. Okay, so let's move further. Okay, so okay, one thing I have forgotten to mention, that is you can see AI and BI are going vary up to 10 power 15 and negative 10 power 15. This is going to be an important one, because I think when I have submitted the first time the code, I have getting the wrong answer. Because if AI is going, if any of the numbers is going to be negative, it would be like oh, suppose one number is negative and other number is positive. Then if we product the two numbers, it will be like we are getting the negative number, and if we perform the modulus with the negative, it will be like something of absurd value. So why not convert this negative to positive? That is, for every I, if ai is going to be negative or bi is going to be negative, just make it positive by with the help of the modulus. Okay, so if you are not going to understand this what I am saying, no need to worry about, I am going to explain in this code. Okay, so let's head over to the code. You can see I have the binary power function in the binary exponentiation that calculates the power of a number efficiently. If you are not aware about this, do check the description link also, description section of the video, that I have mentioned the binary exponentiation tutorial that calculates the power of a number efficiently. Because without knowing this, we are not going to have we are not going to fetch the answer efficiently, because we need to calculate the power with modulus efficiently if the number is going to be very large, if the base or the exponent is going to be very large. Okay, this method is going to calculate in log of min of ab time. Okay, now in the main function you can see I have this an and bn array. Now you can see one slight modification that I have done. If ai is negative, I need to make it positive. So how I have done positive, note that is ai is going to be vary up to minus 10 power 15, that is the minimum one. So I have just added 9 times, that is you can see I have just put the 7 times 9 into modulus and the entire mod, because to make it positive. Okay, that it would be like more than 10 power minus 10 power 50, I need to make it positive. So just add that number which is greater than 10 power 15 around. Okay, so just I have done that if ai is negative. Similarly I have done this for bi. Okay, so that I will not get any wrong answers. Now you can see I have answered initialized as 0, and now I have three terms, that is I've already said product ai into bi, ai square and bi square, and I need to calculate in reverse manner, that is in suffix way. Okay, suffix sum. Now a square is initialized with a of n minus 1 square, and b square is initialized with b of n minus 1 square, and prod sum, that is product sum ai into b is initialized with a of n minus 1 into b of n minus 1 modulus plus, if this is going to be maybe negative, you can also just skip this term, plus mod. Okay, and the entire mod. Okay, now start from I equal to n minus 2, because you can see I have this term like I, it is going up to I equal to 3. So if n is going to be 4, I need to start from I equal to 3. So I will like start from n minus 2, and current answer is 0. What is the term 1? That is ai square into b square. You can see the suffix sum I have basically taken in b square variable. That is ai square. You can, okay, sorry, ai square you can see, and the suffix sum found till now for the bi square, and similarly bi square into suffix sum found for ai square till now, and the twice of product of ai into bi into suffix product found till now, suffix sum product. Okay, so term 1 is going to found this for ai coefficient, and term 2 is going to found for bi coefficient, bi square coefficient, and term 3 would be like product 1 ai into bi plus mod and the entire mod, because so it might be negative. I think if I'm going to skip this one, it will not make any wrong, because I have already make ai and bi as positive. Okay, now I need to do for term 3 one thing more, that is may multiplied by 2 and multiplied by prod sum, that is the prefix sum also. Okay, found till now. Okay, so finally I need to add term 1 and add term 2, but I need to subtract term 3, because it will be like minus twice ai into bi. Okay, now I need to update a square variable and b square variable and prod sum variable, because it is basically the suffix sum variables. I need to update every time starting from I equal to n minus 2 up to I equal to 0. Okay, so a square will be updated like this, b square will be updated like this, and prod sum will be updated like this. That is square of the ai square, sorry ai square, bi square and ai into bi product. Okay, and finally print the answer, because basically I need to find the sum. It would compute the sum in O of n time, you can easily see, and if you use the brute force it would be like O of n square. Okay, so let us wait. Okay, so it is accepted. So if you have any doubts, let me know in the comment section of the video. And as I've already said, binary exponentiation tutorial is already present in the description section of the video. If so, if you are unaware about that, so do check that also. And I will ask the viewers to like this video, share this video, and do subscribe to our YouTube channel for latest updates. Thank you for watching this video.